Hello students, welcome back to my YouTube channel. In this video, I am going to discuss about magnetic dipole in a uniform magnetic field. Magnetic dipole means a north pole and a south pole separated by a small distance, like bar magnet. You see, this is a bar magnet. North pole is one end and the south pole is other end. These two north pole and south pole is separated by a small distance. So we can consider this bar magnet as a magnetic dipole. Okay. And consider the distance between the pole is 2L and QM, that is the plus QM is the magnetic pole strength of the north pole and minus QM is the magnetic pole strength of the south pole. Okay. Then the strength of this magnetic dipole we can express by a term that is magnetic dipole moment. Magnetic dipole moment, smaller m is equal to Qm into 2L. Okay, where the 2L direction is from south to north. So the m direction is from south to north. Okay. So this is the magnetic dipole moment direction of a bar magnet. Okay. So now I am consider a uniform magnetic field in this region. A uniform magnetic field in this region. I am going to place this magnetic dipole here inside it. This is the bar magnet. Okay. Then south pole is here and the north pole is here. Okay. So here you see this, the magnet and the magnetic field is making an angle theta. That means the magnetic dipole moment, this is the magnetic dipole moment and this is the B. These two make an angle theta. Okay. So now you see what will be happen to this dipole. This north pole exert a force in this direction, that is plus Qm into B, and the south pole exert a force in this direction, that is minus Qm into B. Okay, so these two forces are similar to the force exerted on a positive charge placed in an electric field. That means you see this. If a charged particle placed in an electric field E, it will experience a force, that is F is equal to Q into E. Similar to here, the magnetic force is, instead of Q, the pole strength of the magnetic dipole into B. Okay, instead of E, B. E is the strength of the electric field and B is the strength of the magnetic field. Okay. So now you see these two forces are in the opposite direction and it is equal. So the net force acting on the dipole is 0. Net force is 0. That means if a magnetic dipole is placed in a uniform magnetic field, the net force acting on the dipole is 0. Okay. But you see this, the line of action of this force is in this direction and the line of action of this force is in this direction. That means these two forces are acting in the two different line of action. So there is a torque experience on this dipole. Okay. We can calculate the torque. Okay. So this is the magnetic field. Now we can consider the bar magnet. Okay, this is the south pole and this is the north pole. The magnetic dipole moment is like this. This is the M. Okay, and it is making an angle theta. Okay, the line of action of this force is plus Qm in this direction. And there is another force minus Qm into B. Here also B is there. This force is in this direction. Okay. Then the torque acting on the dipole. Tau is equal to force into perpendicular distance between the line of action. So here I am going to draw a perpendicular. This is the perpendicular between these two line of action. This is in this line of action and this is. So this is a perpendicular distance. To find out that, I am going to create a triangle, that is ABC. Okay, if this angle we already consider as theta, so this angle is also theta. This angle also theta. So what about the perpendicular distance? That is BC. Okay, from this triangle ABC, what about sine theta? That is this theta. Sine theta is equal to opposite side, that is BC divided by the hypotenuse. The hypotenuse is the length, that is 2L is the hypotenuse. BC divided by 2L. Okay, from this, what about BC? BC equal to 2L sine theta. Okay, BC equal to 2L sine theta. Now we can substitute the torque is equal to force into 2L sine theta. Okay, 2L sine theta. What about the force? That force is Qm into B into 2L sine theta. What about this Qm into 2L? That is magnetic dipole moment. Okay, so magnetic dipole moment. So the torque tau is equal to mb sine theta. Okay, this in vector form we can write as the torque tau is equal to m cross b. Okay, the direction of the torque is perpendicular to the plane containing m and b. Okay, this is the torque acting on the dipole. Okay, this formula also we can derive from the torque acting on the electric dipole. Okay, so when an electric dipole is placed in a uniform electric field, it will experience a torque. The torque is equal to P cross E. Just change the electric variable to magnetic variable, that is P you change it to M. P is the electric dipole moment, that is you can change it to the magnetic dipole moment, and E you can change it to the magnetic field. Okay, so from this you will get the torque is equal to M cross P. Okay, this is the way also you can find out the torque acting on the magnetic dipole placed in a uniform magnetic field. Okay, then so what about the direction of this torque? This torque try to rotate this dipole in this direction. Okay, so due to the inertia of this dipole, there is a restoring torque is acting in the opposite direction. The restoring torque try to bring back in the opposite direction. That means this torque is the deflecting torque. That is, this is the restoring torque. This is the restoring torque. This restoring torque try to bring back to the original position. The restoring torque acting on a magnetic dipole is I alpha, where alpha is the angular acceleration. So due to the reflecting torque, the dipole deflect like this, and due to the restoring torque, it will try to bring back to the original position. Again, deflecting torque will act, it will try to come down again upwards. That means this dipole is oscillating. It is the dipole is oscillating like this. If you see that, if you like this, it will try to rotate like this. Okay, this you can easily understand by taking a compass and place nearby a bar magnet. You can see that the needle deflect and close toward the bar magnet. If you take it away from the bar magnet, the compass needle come to the original position. Clear? Okay. So when a dipole is placed in a uniform magnetic field, it will oscillate. That oscillation time period we can find. The time period is found out by using the equations. That is the torque and that is the deflecting torque and restoring torque equations. At the equilibrium, the restoring torque, that is the restoring torque, that is the I alpha is equal to the deflecting torque, that is mb sin theta. Okay, what is alpha? Alpha is angular acceleration. So I into d omega by dt is equal to mp sin theta. If theta is very smaller, sin theta is equal to theta. Okay, then this angular velocity omega is, we can write like this, that is d theta by dt. So this equation we can change it like this: d square theta divided by dt square is mp theta. Okay, where theta is the angular displacement. Okay, now do you see this I am taking to this side. I am taking to this side, so I am getting d square theta by dt square is equal to mpi by theta. Okay, this I am taking to this side. So what will get? D square theta by dt square minus mp divided by I theta is equal to 0. This equation is similar to the equation of a simple harmonic motion. Okay, so what is the equation of a simple harmonic motion? If you consider a simple pendulum, if you try to take it to this position, it will come to this, and again it will reach us to this position, again try to go back to its equilibrium position. Like this it will oscillate. Okay, so this is the simple harmonic motion. So that equation is d square x by dt square minus omega square x is equal to 0, where omega is the angular frequency of the simple harmonic motion. Here x is the displacement from the equilibrium position. Okay, so you compare with these two equations. Instead of displacement theta, that is the angular displacement is there. Okay, so if you compare these two equations, we can say that the oscillation of the dipole is a simple harmonic motion and the frequency square is equal to mp divided by I. Okay, then what about the angular frequency formula? That is 2 pi by t, where t is the time period. T is the time period. Okay, this you can substitute it here, so you will get as 2 pi by t all square is equal to mp divided by I. That is 4 pi square divided by t square is mp divided by I. Okay, so from this t square you take it to that side and this all this side. So I by mp into 4 pi square is equal to t square. Take the square root, then you will get the time period, that is equal to 2 pi square root of I by mp. You will get I by mp. Okay, this is the time period of the oscillation of the dipole. By using this formula, you can also find out the unknown magnetic field. You see this, if you square on both sides, t square is equal to 4 pi square I by mp. From this, what about the b? b is equal to 4 pi square I by mt square. Okay, so if you want to find out the magnetic field in a particular region, place a magnetic dipole. That magnetic dipole moment of inertia and magnetic moment should be known. Then the time period you can measure it. By using this formula, you can find out the magnetic field in that region. Okay, this is the thing about the magnetic dipole in a uniform magnetic field. Okay.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like and share.